The last couple of lectures, we've been talking about flow reactors and specifically continuously stirred tank reactors or CSTRs. And one of the things that we've been doing, although not explicitly stated, is talking a lot about liquid phase reactions. And that makes us want to draw a CSTR, something like this, where we have an inlet and an outlet flow, we have an impeller, and then of course we have some liquid level. And when we have a liquid, all we have to do is assume that the density is approximately constant. And what's going to happen then is that if mass is conserved inside of the reactor, which of course it is because we've solved the mass balances, that means that the change in the volume is equal to 0, right? So that automatically assumed if the densities were constant, that the volume was constant. And if that's the case, to operate at a steady state volume, that also implied that the volumetric flow rate was equal to a constant. And that was all fine for liquid phase reactions. But what about gases? Well, let's start to think a little bit about gases. So I'm going to remove that little squiggly line, which is a liquid level, and let's remove those assumptions here for a second. And for a gas phase reaction, of course, also the box is closed. Unless you have some sort of strange, piston cylinder-like reactor, but that's often not the case. Often what happens is that you have a rigid box that some reaction is happening in, and you design the reactor that way. And so when we have a gas phase reaction, that means that the volume is essentially always constant, and the volume equals our container volume. So our volume is forced to be constant. And that can lead us to a question then to ask, well, what factors in a gas phase influence the density, right? And of course, this is a somewhat weird question to think about at the beginning, because in a liquid, the density is only a function of the temperature, right? Like we almost always assume that liquids are incompressible, so pressure doesn't actually help us. But in the gas phase, of course, that's not true. And so if we want to think about the density of a fluid in the gas phase, I think one of the easiest places to start is the ideal gas law, right? Because we know that PV is equal to nRT in this rigid box. And you can forget about the arrows here for a second. And if that's true, and we want to talk about density, right, or concentration, right, that's just a relationship between the volume and the number of moles. So density specifically would be the specific volume, which is V over N, right? And that's just equal to RT over P. So if we look at the variables then that influence the density inside of a rigid container, there are only 3 that we have control over, right? One is, well, maybe 2 that we have control over. We have temperature and pressure, and one that is going to be a function of the reaction that we're looking at, and that is N. And the reason that I say that, of course, is because in the ideal gas law, PV equals N total times RT, right? And we have, that would be N total as a subscript on N in that equation. And so during a reaction, it is very, very possible for the total number of moles to change. So for example, let's look at a reaction that we've considered multiple times so far this semester. We have A plus B goes to C. Well, here you can look at this reaction, and the number of moles on the reactant side are 2, and the number of moles on the product side is 1. And so we can say that the change in the number of moles for this reaction is equal to -1, right? You essentially lose a mole. And at constant volume, if the temperature and pressure don't change, that of course would mean that the density changed, right? And so for us, we have to figure out a way to incorporate that into our equations, especially when throughout this semester we've started by looking at rate laws, which of course have the concentration in them, which is just 1 over the density. And so for the liquid phase reaction, we knew that we could define the flow rate of A that is leaving as just equal to the flow rate, the initial flow rate times 1 minus the conversion, right? So let's say this is for liquids, right? And this is just what we've done so far, almost as a refresher. Well, of course, then we've said that the flow rate of species I is just equal to its concentration times the volumetric flow rate. And so Ca times V equals Ca0 V0, then times 1 minus X. And of course, for the liquid, we've essentially assumed that the volumetric flow rates were equal to each other, which means that they cancel. And then we got to this very familiar expression that Ca equals Ca0 times 1 minus X. And when we're interested in how the concentration changes with conversion and then inserting that into our mole balances, this has been extremely helpful for us in the first couple of homework assignments, as well as the problems that we have been solving in class, okay? And so we've used this a lot. Now, what about the gas phase? So let's have a look at this for gases, okay? So we need to find a relationship between the final volumetric flow rate and the initial volumetric flow rate, because we just said above, the density is going to change. So this expression is going to have to take into consideration things like temperature, pressure, and the change in the number of moles. So how in the world are we going to do that? Well, I'm going to start with the ideal gas law, except I'm not going to write it the exact same way that we wrote it up here, where PV equals nRT. We're going to look at the flow version of this, where now we're looking at the volumetric flow rate of fluid and the molar flow rate of our products and reactants. And so we can say then, instead of PV equals nRT, that P times the volumetric flow rate equals F times R times T. And of course, the F here is the total flow rate in the system. Okay. So what we can say then is that at the very beginning, when we enter the reactor, right? So entering the reactor, we have some initial relationship, which is our initial pressure times our initial volumetric flow rate equals the initial number of moles that are being fed to our reactor times R times T. Okay. So that's what we have at the beginning. So we'll call this, entering. Okay. And now we're going to look at this thing where we're going to say what happens at the end. Well, we're not going to assume that these adjustable parameters are the same. We're going to say, well, fine, PV, right? Both of those things could plausibly change, equals F times RT, which of course is exactly what I just wrote above. But remember that if F is equal to the total number of moles, well, the total number of moles then is just the initial number of moles that we had plus the number of moles that are either generated or destroyed in the reaction. Because remember, for our reaction, the change in the number of moles does not have to be equal to 0. So I'm going to rewrite this equation here. I'm going to say P times the final volumetric flow rate is just equal to F0 plus Fg times RT. And this might bring up a really logical question to you guys. What the heck is Fg? And how in the world are we going to relate that to things that we've talked about in class before, or things that we've talked about in other classes before? So let's tackle this for just a second. So let's think about this not in terms of variables, but let's just put this thing into words, right? So we're going to say that Fg then has to somehow be equal to the moles that have reacted in the system. And when we have reactions like A plus B goes to C, A has kind of been the anchor for all of our calculations. So I want Fg somehow, because remember, we define conversion based on A a lot of the time. So I want Fg to somehow be related to the moles of A that have reacted. Okay, I want that to be part of this expression, because then we can get back to things like conversion. And I'll show you how we're going to do that in just a minute. So now how do we get from moles A reacted to the total number of moles in the reaction? Well, we're going to introduce that by saying, well, we know that our expression has some change in the total number of moles, right, in the reaction. And that's related to the reaction stoichiometry. So then that is going to be related to the change in the number of moles of A. And I'm going to make that the absolute value because we know A is always reacted. So in the reaction. Okay, oops. So I have that this generated number of moles in our reaction is linked to the number of moles of A reacted times the total number of moles in the reaction divided by the moles of A that were in the stoichiometry, right? So maybe this expression would have made even more sense to you guys if I had written it like this. I had almost written it as like a ratio of the moles of A reacted versus its stoichiometry times the number of moles total that that changed in the reaction. So either way that makes sense to you guys, please go ahead and take that. I like it the first way. I also could see how this way can make a little bit more sense. Okay. So now what does this mean, right? Let's put this in terms of variables that we've seen before. Well, to me, this just means that this new variable, Fg, the generated number of moles that are flowing in our system, well, the moles of A reacted, we already know what that is. So remember that we had defined conversion as the moles reacted over moles fed. So that means that the moles of A that have reacted is just equal to the moles fed times the conversion. So that's just FA0 times X, right? That's what this thing is. And hopefully that makes some kind of sense to you guys. And now the change in the number of moles in the reaction is this thing on the that I call delta N, right? Which was related, it's basically the sum of all the reactant stoichiometries, then divided by the absolute value of the stoichiometry for A. Okay, so I'm going to make one more simple substitution, and then we're going to see how this is going to get incorporated. So I want to link FA0 back to the this F0 that I had, because I don't want different initial flow rates just kind of floating around. So we can easily relate those, right? So FA0 just equals the initial number of moles, the total number of moles flowing initially, or the flow rate, the total flow rate at the beginning, just times the initial mole fraction of A. Okay, so those two things are the same. And if we do that, then this expression becomes just Fg equals F0 times YA0 times delta N over the stoichiometry for A times conversion. Okay, and I'm going to put that in this equation here above, where PV equals FO plus FG times RT. And here, I want you guys to kind of see how that works. So when I do that, right, this just becomes PV equals, then this is F0 plus now this thing, right, which was FG. So that's F0 YA0 delta N over the stoichiometry of A times the conversion times RT. And if I do this, I can pull F out, F0 or F naught out of the bracket and get an expression that PV equals F naught times 1 plus F, oh, sorry, I pulled out the F0, YA0 delta N over the stoichiometry of A times the conversion times RT. And this thing that I'm gonna circle is really, really a pain to just carry around in all of our reactions. And it's something that's relatively straightforward for us to calculate, and we'll do that in an example problem in a minute. But that is given a symbol in our book. So it's given the symbol epsilon. I know this might be confusing because this is the symbol that the Thermo 2 book gives for the extent of reaction. So I'm sorry about that. So that's going to be floating around here a little bit. So epsilon, we're going to define as, essentially as this factor that relates the initial mole fraction, delta N, and the stoichiometry of A. And we're going to get this final expression that PV is equal to F0 times 1 plus epsilon x, not extent of reaction, times RT. Okay? All right. So before we do something with this, I just want to open the floor up to you guys to ask some questions. I know that we just did a derivation, but I just want to make sure that this made sense to you guys and that that we're okay to move forward. All right, I don't hear anything, so I'm going to keep going. Now, we said the whole point of this was that we wanted to develop an expression for this volumetric flow rate, and somehow it would be really great to relate it to the entering volumetric flow rate, so we could understand inside of our reactor how that changes. So I'm going to do something that we would have done, let's say in thermo, if we wanted to know the volumetric ratio. I'm going to divide these two sort of ideal gas relationships by one another. So I'm going to divide PV over P0 V0. And so then that equals F0 times 1 plus epsilon x times RT. And for the initial condition, that was just F0 times R times T0. So let's cross a couple of things out that are going to cancel, right? So of course the R's are going to go away and these F naughts are going to cancel. And what we're left with then is 1 plus epsilon x times T over T0. So that means that PV over P0 V0 equals 1 plus epsilon x times T over T0. And from here, there are a couple of different ways that we like to express this relationship. And the first one is explicit in the specific volume, right? Or the volumetric flow rate. Sorry. So the volumetric flow rate, if we just solve for that, would be V0 times 1 plus epsilon x times T over T0 times P0 over P. Okay. And actually, I don't like how that looks that way, so I'm going to leave it like that. So this is one way that we're going to use this expression. Now, so far in our class, we've always assumed that the system is isothermal and isobaric. But we're not going to do that for the rest of the semester as we make the reactors that we consider progressively more realistic and progressively more complex. Another way that it's helpful to rearrange this equation is not just to be explicit in the final volumetric flow rate, but to think about what the ratio is between the initial and the volumetric flow rate. So to get V0 over V, we're also going to use this quite a bit. And if you just rearrange that equation for V0 over V, you get that that's equal to T0 over T times P over P0 times 1 over 1 plus epsilon x. Okay, so that's the second version of this equation that we are going to use this semester. Okay, and these are going to help us now for gas phase reactions where the number of moles are going to change. And so let's revisit our expression for the flow rate, but now think about a gas phase reaction where the volumetric flow rates are not the same. And so remember, we have FA is equal to FA0 times 1 minus x. This is still true. This still comes directly from the definition of conversion and just by applying it to our mole balance, right? In minus out plus generation minus consumption equals 0, right? Because we're operating our CSTR at steady state. So this expression is still fine. And we're going to make the same substitution we made above, of course, right? This is just Ca times the volumetric flow rate is equal to Ca0 V0 times 1 minus the conversion. Well, that means then that Ca, if our volumetric flow rate is not the same, equals Ca0 times 1 minus x times V0 over V. And now you can see why above we actually wanted the ratio between those two volumetric flow rates. And so we can just insert this expression into our equation that we wrote. And Ca then equals Ca0 times 1 minus x, now times V0 over V. And so that was 1 plus epsilon x times T0 over T times P over P0. Okay. And that is our expression for A when, or for in the gas phase, when we allow the density to change, right, from temperature, pressure, and when the number of moles change, right? So this was for gas phase reactions. Okay. All right. Any questions about this? If not, hopefully you can see one of the reasons why we have been solving problems, not just in terms of the absolute concentrations all of the time, but also conversion. We are going to not only need expressions for A, but all of the reactants, and we're going to get them as a function of the conversion. So conversion is going to become a very routine part of our calculations, especially when we're working with gas phase reactions. And if we wanted to consider what would happen for all of the other species in a reaction, not just, you know, reactant A, but the rest of our species are still described by our mass balance, right? For our CSTR, or here for our flow, you know, for a general flow reactor. And so we would get, of course, the same expression we've gotten before, right? Where the flow rate of I has to then be equal to the initial flow rate. So out equals in plus generation, or, you know, you could also say minus the consumption, or what, however you want to do it. But I'm going to say that is minus the change in the number of moles of whatever that species is. And so we know this substitution, right? C times VI is equal to now CI0 V0, now minus. And somehow we have to relate this to A, because we have conversion as the change in the number of moles of A. And we've actually done this together in ice tables before. It might not feel that way, but in some of the homework problems that we've solved in office hours and some of the things that we've done in class, we have to actually think, well, what is the change in the number of moles of A? Well, that's actually pretty easy. That's just V0 times Ca0 times the conversion, right? So that would be the change in the number of moles of A. So how would I relate that in an ice table? Well, remember, that would just be the stoichiometry of species I over the stoichiometry for A. And maybe a way to say this is that, look, if we had A or 2A plus B, what would happen to B? Well, you would consume half as much B as you did A, and that would make this ratio 1/2. Or let's say that 2A plus B goes to C, and we were interested in C. Well, this would be minus, or that would be 1/-2, right? Or minus 1/2. So that would actually make this sign positive. And that would then tell us, oh, the concentration of C then was increasing while the reaction was going on. So this stoichiometry, right, or adding the ratio between the stoichiometry of the all other species than A to the stoichiometry for A is something we've done in our heads in ice tables since ECHE 300. So hopefully, you know, adding it here makes a little bit of sense to you guys. And if we do that, then we could just solve for the concentration of I. And that just becomes, we'll take V0 out. So that's, again, just V0 over V. But now this is times CI0 minus, the ratio of the stoichiometries times Ca0 times X. And we have our expression for V0 over V already. And that is that Ci equals then Ci0 minus these stoichiometries, Ca0 times X, now times V over V0, which, like I said, we've already done. So this is just 1 plus epsilon times X times T0 over T times P over P0, okay? And now we have an expression not just for A, but for all of our reactants as a function of the conversion for a gas phase reaction, which is interesting. Now, your book takes this one step further, and sometimes I like it and sometimes I don't, and I'll explain why in just a minute. So sometimes what your book will do is they define this term theta I, which is equal to Ci0 over Ca0. It's also equal to Fi0 over Fa0, right? Because it's just multiplied or divided by the initial volumetric flow rate. And that's just a constant, right? It's the initial value. So you can see that fraction defined both ways, or that constant defined both ways. And the reason that they do that is that now you can get Ci equals, and I'm going to keep the parentheses really quick and say that this is Ca0 times, or here, let me do this maybe. That would be Ci0 times Ca0 over Ca0 minus the ratio times Ca0 times the conversion over 1 plus epsilon X times T0 over T plus P over P0. And the reason that they do that is that now we have a Ca0 in front or in the numerator of both of those expressions. And so when you do that, we can pull it out. So then that becomes Ci just equals Ca0 times Ci0 over Ca0, which of course is this new thing that just got defined. So that just becomes multiplied by theta I minus the ratio of the stoichiometries times Ca0x over 1 plus epsilon x. Okay. And actually,
there is a small mistake here. There we go.
the example we're going to work on today is that we have the following gas phase reaction in an ideal CSTR at 325 degrees C and 10 bars. We have A plus B goes to C, and we're told that we can assume that reactants are fed to the reactor at the operating temperature and pressure, and we're supposed to determine the concentrations of A, B, and C, as well as the relative volumetric flow rate as a function of the conversion. Assume that the reactants are entering the reactor as equal molar. So the initial mole fraction of A and B are both equal to 0.5. A plus B goes to C, which is what we mentioned just a moment ago. And I know, based on what we've written above, that we're going to have to get to concentration at some point here to utilize the equations that we derived. So to do that, I first want to solve for the initial concentrations of A and B. And I'm going to do that first by just applying this exact same equation that we wrote a minute ago. And the first thing that we can do is look at the initial volumetric flow rate, and we can derive the concentration. So let's do this first, actually. Let's do the volumetric flow rate is equal to F0 times RT over P0. Now, actually, looking at the problem statement, we don't have a molar flow rate that's given to us. So let's make an assumption here. And so let's say that the initial volumetric flow rate is 5 moles per minute. Or is it there? No, actually it's not there. Okay, so let's say it's 5 moles per minute. So we're going to say that F0 equals 5 moles per minute. Okay? And if we want to find the initial volumetric flow rate, of course, then that's just equals to 5 moles per minute times 0.08314 liter bar per mole Kelvin times the initial temperature, which we're told is 325 degrees C, so that's 598.15 Kelvin, divided by the pressure. And of course, we use liter bar here. We're given the pressure in bars, so that is 10. That's equal to 10 bar. So the initial volumetric flow rate then is equal to 24.865 liters per minute. And we can actually check the units if we want to. And then moles cancel, Kelvin cancels, and bar cancels. And we're left with 24.865 liters per minute. Okay? All right. So we now have the initial volumetric flow rate. That's great. So now let's use the same equation to get us to our concentrations. So if we're going to do that, well, again, right, we know that PV is equal to FRT, and P0 V0 is F0R times T0. And if we want to get the initial concentrations, I'm going to multiply both sides by our initial mole fractions. And if I do that, I can actually rearrange this equation, or maybe slightly simplify it first, and say that this is just Fi, right, the flow rate of that species. So Ci0 really just equals Fi0 over V0. And so that is equal to just Yi times P0 divided by RT, 0. Okay? And hopefully that makes sense. And so let's calculate these. Well, Ca0 then equals, we know the mole fraction is 0.5. The initial pressure is equal to 10 bar. We know that, again, R is 0.08314 liter bar per mole Kelvin. And then finally, we again are at 598.15 Kelvin for our temperature. And again, we'll look at the units really quick. Kelvin cancels, bar cancels, and that gives us an initial concentration for Ca0 as being equal to 0.10 moles per liter. And the mole fraction of B, of course, was also equal to 0.5. And so that's going to give us the exact same number. So I won't waste our time here by also solving for that. Okay? So this is good. So we have our initial volumetric flow rate, we have the initial concentration of A, and we have the initial concentration of B. And what the problem asked us to find was to find the volumetric flow rate and the concentrations of A, B, and C just as a function of the conversion. So this is only asking us to apply the equations that we just derived. And the first and easiest one is to do the volumetric flow rate. And remember, we derived that V over V0 equaled 1 plus epsilon x times T over T0 times P0 over P. Okay? Well, in our problem statement, we're going to assume that the reactor is operated isothermally and isobarically, at least in this problem. And if that's true, well, this simplifies rather nicely because isothermal, that goes away. Isobaric, that goes away. Now, during the course of our semester, we're going to assume that reactors are isobaric almost all of the time. You guys will get a couple of homework problems on it, but we won't extensively discuss non-isobaric reactors in class. we will lift the assumption of isothermal quite a bit as we move forward. So just to give you guys a heads up for what's coming. So we're left with this expression where V over V0 is 1 plus epsilon x. It's a very common thing or a common place for us to get to. So let's calculate epsilon, okay? And remember, epsilon we defined as YA0 times delta n over the stoichiometry of A. So if we do that for this problem, that was 0.5. For A plus B goes to C, delta n is -1, right? Because we have 1 mole of products and 2 moles of reactants. And the stoichiometric coefficient here for A, and I apologize, right? It was the absolute value of the stoichiometric coefficient for A. So the stoichiometric coefficient is -1, and the absolute value for that is equal to 1. And so that gives us an epsilon value in this problem equal to -0.5. So the volumetric flow rate here is just V0 times 1 minus 0.5 times the conversion. Okay, so there's our expression for the volumetric flow rate. And let's have a look at that. I mean, obviously, it's just going to be a straight line with the conversion. And here I plotted V over V0. Okay, and so this will just change linearly with conversion based on our equation. So that should make some kind of sense, right? Given the functional form here, you would expect this to just be a straight line with a slope equal to -0.5. So that's exactly what we found. And now let's apply our concentration equations. And we know that Ca equals Ca0 times 1 minus x divided by 1 plus epsilon x times T0 over T times P over P0, right? And again, these are, this will be isothermal and isobaric. So that gives us an expression for the concentration of A as being equal to Ca0 times 1 minus x over 1 minus 0.5 times x, right? Because epsilon was minus 0.5. All right, so there's our expression for Ca. And now let's do the same thing for Cb. Well, we said that for all species that Ci0, right? So let's apply this, right? So we said Ci was equal to Ci0 minus the stoichiometric coefficients times Ca0 times x over 1 plus epsilon x times T0 over T times P over P0. So let's apply that here to B and C. So if we do that, then Cb would equal just Cb0 minus the stoichiometric coefficient for B over the stoichiometric coefficient for A times Ca0 times x over 1 plus epsilon x times T0 over T times P over P0. And again, those go away. In this case, the stoichiometric coefficient for B over A is just -1 over -1. So that's equal to 1. And so we get this expression then that Cb equals Cb0 minus 1 times Ca0x, right? Ca0x over 1 minus 0.5 times x, right? So there's A, there's B. And lastly, let's apply that equation to C. And then Cc would equal Cc0 minus the stoichiometric coefficient for C over A times Ca0 times x over 1 plus epsilon x times T0 over T times P over P0. And again, those go away. Now in this case, right, the stoichiometric coefficient of C over A is equal to 1 over -1, right? So that's -1. And CC0 is, let's say, equal to 0. We often don't start with the product in the reactor. So that means that CC equals, this becomes -1, which is +1, Ca0x over 1 minus 0.5 times x. And there's our expression for the concentration of C as a function of the conversion. And if we look at these, Ca and Cb are equal to each other, and that makes sense because they came in at the same concentration and their stoichiometry is equal to 1. So it would make sense that those two concentrations are the same. And then, of course, C is constantly increasing over the course of our reaction. Okay. Now, one of the really interesting things about this is that the concentration of C is going to reach a value that is essentially twice the concentration of A and B. And at first, that might seem weird because in our previous examples, the concentration of the product, right, in the liquid never got above the concentration of what you initially fed, especially when the stoichiometry was equal to 1:1. But it can do that in this case because the pressure and the temperature have to be equal to a constant, right? If you think about this, that PV equals nRT in a reactor, or maybe a better way to think about it is even in terms of the flow rates. So equals F times RT, right? And if you think about what's happening inside of our reactor, well, the concentration is just like N over V, right? Or F over V in this particular case. And so as the number of moles are decreasing, the volumetric flow rate is also decreasing, right? So F over V ends up just being P over RT. And in our problem, we assumed that the pressure was equal to a constant. We also assumed that the temperature was equal to a constant. And what that means here then is that if you plot the sum of the concentrations with conversion in this gas phase reaction, it's a constant number, right? That's the y-axis here, is the sum of Ca plus Cb plus Cc. And it's always going to be equal to the same number because the temperature and pressure don't change. So that's a really interesting little thing that happened in a gas phase that wouldn't really happen in a liquid phase. And it's not a fact that we're going to use to our advantage a lot, but I've talked during the course of our semester about looking at a solution and trying to make sense of it, because you often get a functional form or you get a plot and you think to yourself, okay, I have the answer, but how do you know if it's right or not? And when you first see something like this, where the concentration of C is greater than A at the beginning, and 1 mole of A became 1 mole of C, that might not make a lot of sense. But then if you step back and think about what's actually happening, that you have a rigid box, that the total concentration has to be equal, well, then this makes total sense, because once you get to 100% conversion of A, you've consumed all of it. And so then the concentration of C must be twice as much, which is not something we would have thought of before. And of course, that's only something you'd have for a gas phase reactor.